we're going to be drawing a Boltzmann distribution using molecular speed on the x-axis for methane and neon at the same temperature. Methane is CH4, neon just Ne. CH4, if we look at our periodic table, is going to be 12.01 for 1 carbon plus 4 times 1.008, 16.04 grams per mole. While neon will be 20.18. So molecular speed and incidentally, I'm sorry for not mentioning this earlier, molecular speed and molecular velocity are equivalent terms. So speed might be 55 miles per hour in a car. Velocity is 55 miles per hour east. So velocity has a direction, it is a vector, but the terms speed and velocity in this course are interchangeable. Now, so what we're going to do, and I'm going to save some space for a second example over here. So velocity or speed goes on the x-axis, fraction of molecules goes on the y-axis, and let's do 2 different colors, but let's see. I'll do methane first, and all we need to know is that since methane has a smaller mass, each particle and a mole of it incidentally, then it's going to be, oh, that's a terrible one. It's not supposed to be nearly that sharp, but it will do. And this has to go all the way back to the x-axis. The other one has to go all the way back to the x-axis as well. There we go. So we will say that the one with the peak and the average at the lower velocity must be neon. And the one at the higher velocity, and higher meaning farther along the x-axis, must be methane. Now, if instead we were to ask the question for draw a Boltzmann distribution using kinetic energy on the x-axis, for methane and neon at the same temperature, we would draw kinetic energy on the x-axis, fraction of molecules, on the y-axis, and because they're at the same temperature, my curves are terrible today, but they will suffice. So what we would just say is, since they're at the same temperature, kinetic energy average and the overall distribution is the same for both methane and neon and any other gas. So don't accidentally draw 2 different curves for these 2 substances.